this video, we're going to learn all about transformations. Now, some of this will be revision from last year, but a lot of it will be new to Year 12. So let's start with the general language. Suppose we started with a pre-image. Now, pre-image is like the base function. It's saying there was a graph. In this case, y equals x squared. So this is what we call our pre-image. Now, the arrow, we'll just tidy that up a little bit. The arrow that you see there is maths language or maths notation for maps onto. Okay, maps onto. And that word onto is really important. So that arrow means maps onto. Now, the last thing, so our slightly more complicated graph in this case, we would call the image. So basically, when we talk about transformations, we're going to say we started with a graph. We did a whole bunch of things to it. We might have dilated it, reflected it, or translated it, and we'll remind you what all those words mean in a moment. We've done a whole bunch of things, and then it became a new graph, or it became an image. So when we're talking about a transformation, we'll often talk about the pre-image maps onto the image. Now, let's look at transformations in the context that you already know. Suppose we had the graph y equals a outside of x minus h squared plus k. So this is just, I suppose, our turning point form, as you would have remembered it from when we first did quadratics. Well, that letter a out the front has a more formal definition. We call it the dilation factor from the x. So we'd say that this has been dilated by a factor of a from the x-axis. So that's not new, that's back from year 11. And you may remember that this h here is what we call our translation. So this has been translated h units in the positive x direction. So you'll often remember when you were trying to find a turning point, we might have said things like it's the opposite of what's in the bracket. It's the opposite to the sign you see. In the example image above, so in here, we've got a turning point of positive 1, 3. So keep in mind here, this is x minus h, and we'll go into more detail in this video as to why that's the case as well. Finally, we would have seen this k. Now, we know that this is what shifts the graph up. So we would say that this is translated k units in the positive y direction. So this one we don't have to worry about changing the sign. We know if it's plus k, it's physically gone up. So these are some basic transformations that hopefully you remember from last year. And if not, that's okay, because we'll go into Desmos and we'll have a look at how these affect the pre-image x squared when we apply these transformations to them. So we've got our basic graph or our pre-image y equals x squared, and I've put in some animations here for a, h, and k. So you can see on the left of screen that at the moment my a value is 1. Now watch what happens when we alter the value of a. So as a is getting bigger, that graph is being pushed in towards the y-axis. So we would say it's being dilated, in this case, by a factor of 6.92, because that's what I've let my a be equal to. And you'll see that as that factor gets bigger, the graph gets more and more narrow. Now that's true for a quadratic, but if you notice what happened there, if a is a negative value, this graph flips down. We'd call that a reflection about the x-axis. So we'll play around with that, but you can see that this is basically going to govern how wide or how narrow the quadratic is. Now this is very true for quadratics. It behaves slightly different for other curves, but it's a good way to think about it as it's going to make it wide or narrow. The other thing that we always look for is if it's positive, the graph will be positive. If it's negative, it will be reflected about the x-axis. Now we're going to play around with the value of h. Now when h is positive, so in this case we would have x minus 1 or x minus 2, you'll see it moves to the right. When h is negative, it moves to the left. Now, rather than using the word moves, which can be a little bit ambiguous, we would say that this graph is translated. The reason why it's translated is because the entire graph, every point on it, is moving. And we're all moving by same static amount to the right or to the left. So one way to think about this is that it's not getting narrower or wider. We're physically picking it up and moving the entire graph. Now, we can revert that back to 1. And now let's play around with the value of k. Well, this is a translation in the positive y direction. So now we can see that it's moving up and down. Because we set h equal to 1, you can see that that turning point is still occurring on x equals 1. And the only thing that's happening is that this graph is shifting up or down. I know that it looks like it's getting a bit wider, but that's simply a matter of perspective. The entire graph is just moving up and down. Now that we have a good idea of what all these words mean, we're going to introduce a new transformation. So the new transformation is going to be y equals a outside of, we've got our x minus h plus k, but a new factor n. Now here, where I see the n, I would describe it as being dilated by a factor of 1 on n. I need to write it as its reciprocal. So we're being dilated by a factor of 1 on n. Now this isn't from the x-axis, it's actually from the y-axis. Now remember, when the value of a was negative, the graph would reflect about the x-axis. So it would rotate down, it would flip down. When n is negative, we actually flip about the y-axis. So I'll show you what that looks like now. So we can see our graph here. We've set the value of a to 1, so it doesn't matter. And we've set the value of h and k to 1 as well, so that this has a turning point at 1, 1. Now watch what happens when we increase the value of n. So you can see that that graph is going to get more narrow, just like it did with a. Here though, I wouldn't say that we've dilated by a factor of 4.75. I'd say we've dilated by a factor of 1 on 4.75 from the y-axis. Now when we unpack this in a little bit more detail, you'll understand why. But watch as we play around with that. So similar effects so far, but as this gets into the negatives, you'll see that this actually rotates about the y-axis. Now it wasn't so obvious there, but watch what happens when I get rid of these brackets. So you can see that once I do this, the turning point has actually flipped. I'll zoom in so you can see a little bit more clearly. So as we get into the negatives, there's the turning point now on the other side. So we're flipping about the y-axis. Imagine you pinch that y-axis and began to spin it in your hands. That's what's happening when we say that we've reflected about the y-axis. So as it gets positive, we'll flip to the other side. Now everything that we've done so far is true not just for quadratics, but for any function. And so more broadly, if we took the function f of x, so that can be any function, and we mapped it onto this big thing, we would look at this and say, well, if I multiplied everything by a, I would be dilated by a factor of a from the x-axis. Keep in mind here that if a was less than 0, so if this was the case, we would say that we were reflected about the x-axis. Now, my value of n here, we would say we're dilated by a factor of 1 on n. This time it's from the y-axis. Now this is what's brand new to the course in Year 12. So you can imagine that most of the difficulty you'll experience will be with this. If n was less than 0, so if n was a negative number, then this graph would have been reflected about the y-axis. Now again, we're going to unpack even more detail what this means, but a couple of things to keep in mind is that we can see that the n is out as a common factor. If I saw f of 2x plus 1, I would need to make that f of 2 outside of x plus a half. So if I'm trying to analyze the transformations, I need to take that out as a common factor. Otherwise, I might mistakenly think that this has been translated 1 unit to the left, when in fact it's only been translated a half unit to the left. So keep that in mind. You'll also notice, as I said, the general equation has a minus in it. So if I see a plus, I must have been taking away a negative. So always do the opposite of what you see for that translation there. So in this case, it's been translated h units in the positive x and k units in the positive y. Let's talk about some translations. And we'll start with translations in the x. Imagine I did have that basic parabola y equals x squared. Well, the turning point, if we imagine it, would be 0, 0. So what would happen if y equals x squared, my pre-image, mapped onto y equals x minus 1 squared? Well, we're saying we'd pick up that entire graph, so let's maybe do a before and after. The entire graph gets picked up and moved to the right. So that 0, 0 is now 1, 0. And everything got moved to the right. Now, if we're imagining we took each point, let's take a point here. Well, that would be negative 1, 1. And this point here would be 1, 1. Because if it's y equals x squared, I just sub in those x's to get the y's. Well, what does that point become? What does this point become? Well, negative 1, 1, if I moved it to the right in the x direction, then negative 1, 1 would become negative 1 plus 1. But the height of this graph won't change, so the y value can't change. And so this actually gives me 0, 1. The point 1, 1 becomes 1 plus 1, 1. So it becomes 2, 1. Oops. So as a general rule, if I'm thinking about what's happening to each coordinate, then my xy would map onto, so my xy would become x plus h y. But what's confusing about this is that my f of x would become, whoops, let's just undo that circle. My f of x would become x minus h. Remember that inside there, that x minus 1, we'd need to remember that it's shifted to the right. But the physical coordinate would of course be added. So that's a subtle distinction. We describe this as being translated h units in the positive x direction. Okay, so what would happen with our plus k? Let's imagine what happens there. My pre-image y equals x squared drawn up here, and this time I want to say that we shift everything up 1 unit. So I'm going to say that y equals x squared maps onto y equals x squared plus 1. If I shifted that up 1 unit, then what I'm going to get is something that looks like this. So each unit moves up. Now if I had drawn that really accurately, it all would have moved up by the same amount. But negative 1, 1 still occurs at negative 1 in the x, but should now be 2. 1, 1 should be 1, 2. So more generally, what I'm saying here is that x, y, any point, so a coordinate, maps onto x, y plus k. And f of x maps onto f of x plus k. Think of it as like it's being added outside the brackets. The function was to square root something, or it was a hyperbola or a truncus, or if it was a quadratic or a cubic, anything that's added after that would be a translation in the y. We can describe this as being translated k units in the y direction. Okay, now we're going to move on to dilations and reflections. So as an example, I'm going to use y equals x squared again as my pre-image. So imagine we're mapping y equals x squared onto the graph y equals 2x squared. Well, we know that x squared is going to be nice and wide and 2x squared is going to be more narrow. But the turning point for this is still 0, 0. So although it's going to be more narrow, it's not going to be as consistent as the other two were. The higher up you get, the wider these two things will be, or these two graphs will be. But right at the bottom, toward that 0, 0, they actually share that point. So if we look at 0, 0, we may not realize what's happening there, because 0, 0 just mapped onto 0, 0, so that doesn't tell me much. But let's think, what did this point 1, 1 map onto? Well, what is the y value when x equals 1? Y equals 2 times 1 squared, so that's going to be 2. So I'll see that 1, 1 mapped onto 1, 2. See if we can establish a pattern. The old position 2, if it's y equals x squared, would have been y equals 2 squared. So it would have been 4. Well, what is that in our new graph? Y equals 2 times 2 squared. That's 2 times 4, which is 8. So I've got the position 2, 8. So what's happened that my 1 became a 2 and my 4 became an 8? Well, these points have actually doubled. And the x points haven't changed, it's just the y points that have changed. So what we're really saying here is to go from x squared to 2x squared, we have dilated by a factor of, in this case it's 2, from the x-axis. Now why is it from the x-axis? Because we're pushing the graph up, so we're starting down here at the x direction and we're pushing every point up. As a general rule, instead of 2, let's just use a. And we can say that xy maps onto, well, the x's didn't change, but the y becomes ay. So we have to multiply every y value. The reason why we doubled it is because our example was 2. And x squared became 2x squared because the function notation here is that f of x becomes 2f of x. Or, more broadly, f of x maps onto a f of x. Now, if there was a reflection, so let's just do a side note. Imagine if a was negative. Imagine if, as a side note up here, we said, what would it look like to be reflected about the x-axis? Well, remember that a governs those reflections, and a multiplies the y values. So xy would become x negative y. Hold all the x values still and negate every y value. F of x would become a negative f of x. So now let's have a look at what happens when we introduce n, when we dilate from the y, and you'll realize exactly why it's important to treat this or to describe this as 1 on n. So I've got my graph of y equals x squared. This time I want y equals x squared to map onto y equals, what if the 2 was inside the brackets? So in other words, I'm saying f of x becomes f of 2x. Well, if the 2 is inside the brackets and everything is squared, 2x times 2x is 4x squared. So my image is actually quite a lot more narrow than before. Now, my original point was 0, 0, and that hasn't changed. But my value for 1, 1, if I subbed 1 into 4x squared, I'll get 1 all the way up there, 1, 4. So when I saw this 2, and I said it's dilated by a factor of, a half from the x-axis, this isn't immediately obvious when I'm looking at this. But let's look at things from the y perspective. So y equals 4x squared, sure. But if the old y value was 1, as we can see there, where is my new image? Where is y equals 4x squared equal to 1? Well, if I divide both sides by 4, x squared equals a quarter. And if I square root the graph, x is plus or minus a half. So this is actually pushing in so that I've got the point. Now it's a little bit hard to see, but that point there is 1/2, 1. Well, there was an old point which was 2, 4. So let's think, well, what's my new point? If I'm treating this as being pushed in, so it's from the y, so we're pushing out or we're pushing in, then y equals 4x squared, we're saying, well, where is that equal to 4? I did have an old point when y was 4, x was 2. Well, now when y is 4, x squared is equal to 1 and x is equal to 1. So what we're saying here is the old value for x is 2, the new value is 1. The old value for x was 1, the new value is a half. What we're saying here by subbing a 2 inside is that we're dilating by a factor of a half from the y-axis. So we describe this as dilated 1 on n from the y-axis. Functionally, f of x becomes f of nx. Now, that's 1 on n, remember? But it would look like it's just a whole number in there. Because it's 1 on n, that point xy doesn't stay xy. The y value, remember, stayed the same. But the x value is x on n. Okay, or it's 1 on n times x. So this is where that dilation gets tricky. If you saw it inside the brackets, you need to describe it as 1 on n. If it was a reflection in the y-axis, so if that was negative, you'd see that the x-coordinate would become negative, and you'd see a negative inside the brackets. So, that's a lot of information to digest, but let's have a look at what it looks like in practice. We're being asked to describe the transformations that have occurred to the function, so this has occurred to a function, from the graph of y equals x squared to this graph. So the context here is that it came from this to that. So here is my pre-image, y equals x squared, and here is my image. Well, the first thing to do is to take this out as a common factor. I can't stress that enough. So we're going to say that y equals negative 2 outside of 4, taking it out as a common factor, x minus 1 squared plus 3. And what mapped onto that? My pre-image of x squared. So we've redefined our question into something a bit more digestible. Now we need to describe the transformations. And oftentimes this will actually say describe the sequence of transformations, which means you need to give them in order. What's happened here? We're going to think Dr. T means do your dilations, reflections, then do your translations. So let's start with dilations. I can see there's a dilation here of 2 from the x-axis. I can see that there's a dilation of 4 from the y-axis. I've taken it out as a common factor. I can now see that there's a translation of 1, but before I do that, I'll need to deal with this negative. It's on the outside, it affects the A, so we would say that this is reflected about the x-axis. After that was happened, we've translated 1 unit in the positive x direction. Now some people might say 1 unit right along the x-axis, and that's fine, but just be careful when you're doing that. If you're saying right and left, don't say positive or negative. Do one or the other, because if you said left in the negative x direction, that's actually moving to the right. So the final thing to describe is this plus 3. So we would say that it's been translated 3 units in the positive y direction. Let's just fix that up, sorry. In the positive y direction. So that's it. We've described the sequence of transformations that took the graph y equals x squared to the graph y equals negative 2 outside of 4x minus 4 squared plus 3. So now it's time to test your understanding. For example 2, we're told that the graph y equals x squared is transformed, okay, so this must have been the pre-image, so that its equation becomes this. So these are my two things. And equation becomes tells me that this is my image, this is my pre-image. Define the transformations which have been applied to y equals x squared. So the question is, define the transformations. Pause the video and give this a go now. So now that you've given it a go yourself, I'll go through the answers. Remember that we first need to take this out as a common factor. So I'm actually going to say that this graph is 1/2 outside of 2x plus 3 over 2. Because if I'm taking it out as a common factor, I do 3 divided by 2 equals that. The whole thing is squared, and we take away 4. Remembering Dr. T, we would say that this has been dilated by a factor of 1/2 from the x-axis. It's been dilated by a factor of, it's also 1/2 because I need to describe it as 1 on 2. But this one is from the y-axis. It's been translated 1.5, so 3/2 units, in the negative x direction. Now why is it in the negative x? Because there's a plus there. So this must have been x minus -3 on 2. It's also been translated 4 units in the negative y direction. So this is one key skill. One of the key skills is to describe the sequence of transformations which take the graph of a pre-image to the graph of an image. But another thing which we might have to do is actually apply these transformations. So looking at example 3 here, it says the graph of g of x equals square root of x undergoes the following transformations. Now, if it undergoes these transformations, we're going to assume that it does that in that order. So that's a usual thing that's okay to assume. Usually in the exam, it would say undergoes the sequence of transformations, and the word sequence implies a pattern or an order. So we're going to apply these each one at a time. Let's start with what we know of our pre-image. G of x equals root x. Now we need to translate 2 units to the right. Okay, well, g of x would become g of x plus 2. Remember, it's the opposite of what we see. So that means the square root of x becomes the square root of x plus 2. We need to dilate by a factor of 3 from the x. Well, okay, that tells me that this g of x would become 3 g of x. So square root of x plus 2 becomes 3 times the square root of x plus 2. If we're dilating by a factor of 1/2 from the y, well, g of x would become g of 2x. So remember here that if we're dilating from the y, we have to take the reciprocal of what we read. We have to flip it. So I did have 3 square root x plus 2, but now I need to take this x plus 2 and double it. So it's 3 times the square root of 2 outside of x plus 2. So please don't ever write 2x plus 2, because actually it's 2x plus 4. Remember that it's got a common factor. If we're translating 1 unit down, so 1 unit down is nice and easy, because g of x would become g of x minus 1. So this whole thing just becomes 3 root 2 x plus 2 minus 1. Now a reflection in the x-axis means that g of x becomes minus g of x. We've got to multiply the whole thing by negative. So not only does this, so imagine I had brackets around that and I said multiply the whole thing by -1. Sure, we'd have -3 root 2 x plus 2, but we'd also have a positive 1. So applying these transformations, you can see, can get quite tricky. I strongly suggest that you do each of them one step at a time to avoid making any mistakes. Now we can also use our understanding of transformations in order to sketch graphs. I know many of you, when you're learning maths, you often get confused between the many different types of graphs. And the most common question I get as a teacher is often asked, well, how do you know all the shapes? Now, the truth is I know some very basic shapes. I know the general form of a graph, and most of the time I just apply the transformations. So when people are like, well, how did you know it goes down? How did you know it was flipped that way? It's always because I've looked at the transformations. For instance, Suppose in example 4 we're asked to sketch the graph of f of x equals 4 over x plus 5 minus 3. So this is what we're being asked to sketch. In my mind I'll say, oh well, that's just going to be a hyperbola because it looks like the one on x. And in fact, if I didn't know that, this question even tells me that the base function or the pre-image was 1 on x. So all I'm going to do is then think, well, has it been squashed? Has it been moved? Once I've done all that, it's asked me to describe the sequence of transformations. So not only has it said sketch the graph, but also describe the sequence of transformations that have occurred from the base function 1 on x. So if you remember, we've got 4 over x plus 5 minus 3. Okay, well that 4 is telling me that it's positive. The general shape of the graph in my mind was correct. However, we've moved 5 units to the left and 3 units down. So previously we might have used h and k to describe the asymptotes for x and y respectively. That's because the original asymptotes were 0, 0. Well, now I've got an x asymptote at -5, so I'll get out my ruler and say, okay, well that can be x equals -5. And I've got a y asymptote at -3, so it's shifted down. So we'll just fix that to 0 degrees and drop it down a little bit lower just for the shape. There we go, y equals -3. Now, the general graph will have that traced shape. I know this one's fine, but what I don't know are my x-intercepts. Because this asked me to sketch, I do need to be careful about this and I do need to show them. So, in order to do that, remember my x-intercept will occur where y equals 0. So I'll simply do this in black. Where does y equal 0? 4 over x plus 5 minus 3 equals 0. So 4 over x plus 5 equals 3. I'm going to put that over 1 because that's just 3. The reason why I'm going to do that is a common way to solve this equation is to just flip both fractions. So x plus 5 over 4, so I raised the left side to the power of -1. And if I do the same to the right side, I'll get 1/3. So that when I multiply by 4 now, x plus 5 equals 4 over 3, and x equals 4 over 3 minus 5. 5 as a fraction of 3 is 15 over 3, so 4 minus 15 is -11 on 3. So that gives me this here. -12 on 3 would be -4, so I know it's going to be something like that. -11 on 3 and 0. My y-intercept occurs at f of 0. So that's just 4 over 5, because my x was 0, minus 3. So 4/5 minus, we could think of 3 as being 15/5. So 4 minus 15 would be -11 on 5. So that's a little bit, I suppose less than a little bit even more less than -2. So it's going to be down here, we'll say that that's 0, -11 on 5. I'll join up my shape. Try to be a little bit more consistent. It's a bit hard with the digital pen here, but that's about close enough. So I've sketched this graph. I've labelled some critical points. I'll label the graph itself and say y equals f of x. And once I've done this, I now need to address the second part of the question. The second part of the question was describe the sequence of transformations that have occurred. So we'll do this on a screen with a bit more room. So I had 1 on x, and it became 4 over x plus 5 minus 3. Well, that 4 we would call dilation, or we'd say it was dilated by a factor of 4 from the x-axis. We've got a plus 5, so we need to think this is going to be translated 5 units. Remember that asymptote went to the left, so 5 units in the negative x direction. And the minus 3, well, this has been translated 3 units in the negative y direction. So there we have it. We sketched the graph and we described the sequence of transformations. Let's see if you can give example 5 a go now. So we need to sketch the graph of y equals minus the square root of x minus 4 minus 5. So this is a square root function. So you can go through your notes, remember what that generally looks like. You need to apply the sequence of transformations so that you can sketch that graph and describe the sequence of transformations here. So again, sketch the graph and describe the sequence of transformations. Pause the video, give it a go, and we'll do the solution in a moment. So this graph was actually very simple to sketch. It was reflected about the x-axis, so instead of doing that, it did that. So I dropped it down. The endpoint was 4, -5, and so we can see that there were no x-intercepts. An example like this is a great way of how someone with good understanding of transformations will be rewarded in the exam. You won't have to waste time trying to find x and y intercepts because you can see that they're not there. So how do we go with the second part of this question to describe the sequence of transformations? Remembering Dr. T, there are no dilations, but there is a reflection. So this was reflected about the x-axis because it was outside the square root, outside the function. So reflected about the x-axis. It was translated 4 units to the right. And it was translated 5 units down. So there we have it. We've sketched the graph and stated the sequence of transformations. Now, sometimes we're presented with a pre-image that is quite complicated, and we need to take it back to a very basic image. In this case, we're asked to find a sequence of transformations, so that's what I need to do, find a sequence of transformations, which takes my pre-image, which has had all this done to it, to the graph of my image. So we're always looking for to the graph of. That tells me where the image will be. So find a sequence of transformations. Okay, well we started off with y equals 3 over x minus 1 squared plus 6. So the first thing that I could do, because the sequence can be of any choosing that I like, the first thing I could do is subtract that 6. Because I want to get rid of everything, so I'm left with 1 on x squared. Well, if I subtract the 6, so I'd be thinking, minusing the 6 will give me y equals 3 over x minus 1 squared. So the first thing I did was translate 6 units in the negative y direction. Okay, so now I've got y equals 3 over x minus 1 squared. Okay, well the next easiest thing to do might be to translate and get rid of that negative 1. So to get rid of it, I'd need to have a plus 1. Well, if I wanted to plus 1, then that would become y equals 3 over x squared. But plussing 1 is translating, so we need to translate 1 unit, it's plus 1, so it's in the negative y direction. Sorry, that would be the negative x direction, of course. Nearly there. We have y equals 3 over x squared, and we want to get rid of that 3. So to do so, we could times by a third. So that would certainly get rid of it, and that would have y equals 1 over x squared, what we want. But timesing the whole thing by a third is doing what? Well, it's dilate, so we'd need to dilate by a factor of 1/3 from the x-axis. Now that we've got here, we're done. And my answer would be that sentence, and that sentence. It's really important we do these one at a time. So, before I do the next answer, I want you to try it yourself. How do we take the graph here, so describe the sequence of transformations which takes y equals 5x minus 1 all squared plus 6 to just the graph of x squared? How do we undo all these transformations? Because you are working backwards, it might be best to deal with the translations first. However, if you want to deal with the dilations, and there is one inside the brackets like we see here, make sure you take it out as a common factor. Okay, so first thing we might do is get rid of that 6. So, we are going to translate 6 units in the negative y direction. So just excuse my shorthand as I get you to correct your answers here. So that would become y equals 5x minus 1 squared. Now, I'd like to get rid of that dilation. And if I was going to do it in order, I'd need to take it out as a common factor. However, this is also perfectly fine for me to deal with translations first, as long as I'm consistent. If I want to deal with that, take it out as a common factor. If I don't want to deal with it, I can just add 1. So I will translate 1 unit in the negative y. So that becomes y equals 5x squared. Finally, to get rid of that, I want to times by a fifth. So timesing by a fifth is dilate 5. Okay, or dilate by a factor of 5. From the y. Now if you did take that out as a common factor, so let's imagine that we were down here, and I'll do it as an alternative. So this is an alternative solution, is that we could have said, okay, y equals 5 outside of x minus a half, sorry, a fifth is what I mean to write there, all squared. So to get rid of the 5 now, I would still dilate by a factor of 5 from the y. So that would be y equals x minus 1/5 squared. But now the final translation would be 1/5 units to the right. So it would be translate 1/5 units to the right, or in the negative x direction. Now finally for this video, I'm just going to show you a very common exam question in exam 1. Suppose we had to sketch the graph and it looked like this. Well, that's a horrible graph to sketch. So we actually need to divide it, and we need to make use of polynomial division. So suppose I said 3x plus 2 is divided by x plus 1. Well, let's start by dividing my leading terms. So we think divide. Okay, that's the first thing. So 3x divided by x is 3. Now once I've done that, I'm going to think multiply. So 3 times x, 3 times 1 is 3x plus 1. So once I've done that, I'm going to subtract. The way we deal with polynomial division, think divide, multiply, subtract, and then just keep going. So 3x take away 3x is 0. That's good. That's what we wanted. 2 take away 1 is 1. So what I'm saying here is that x plus 1 goes into 3x plus 2 3 whole times and 1 remainder. So what does it mean to say 3 times and 1 remainder? Well, it means that 3x plus 2 over x plus 1 equals 3 wholes and 1 remainder. Well, that's something that's a lot nicer to sketch. Y equals 1 over x plus 1 plus 3. That's certainly something I can sketch. So I'm not going to do it in this video because I think you're all very capable now of sketching that graph. You can use your CAS calculators to double check it. The sequence of transformations that have occurred here is that we've translated 1 unit in the negative x direction and 3 units in the positive y direction. There's so much that we've gone through in this video, but I just want you to make sure of this little cheat sheet that we made here. Ensure that you've got that in your notes because it's going to serve as an excellent revision tool. Remember that if I'm translating in h units in the positive x direction, my function, it'll appear as a minus h. But the coordinate, the x will actually become x plus h. If I'm translating k units in the y direction, it'll appear outside my function, and it will just be as it appears. And the coordinate will be that I'm actually changing all the y coordinates, but keeping the x coordinates the same. Dilations work the same way. If I'm dilating from the x-axis, well, I'm actually multiplying all the y values by a. So that xy becomes x negative y or xay. But f of x will have the a outside. If it's a negative, it's a reflection. Remember that if I saw f of nx, so f of 5x for instance, we describe it as being dilated by a factor of 1/5. So we've got to describe it as its reciprocal, because what's happening really is that we're taking the x value and multiplying it by 1 on n. So it's really important, this one in particular, but the best advice I can give you is to practice, practice, practice.